Hello. Hello. How's it going? Good afternoon, Potato. Happy Friday, Rue. I hope you guys are doing well. I'm certainly very happy it's Friday. You know what I want to do today? Well, I want to get outside. I want to take a walk or something. But I also want to watch a movie. There's a movie out on Netflix. It has a depressing title, but it looks really interesting. It's called I'm Thinking of Ending Things. Have you guys seen that one? It's new on Netflix. The director or writer, really famous. What's his name? Like Kaufman or something? He's the same guy that did Being John Malkovich. Some other cool stuff. But I want to see this movie. I'm Thinking of Ending Things. That's what it's called. If you watch the trailer, it looks really trippy. Okay. The hat is back. The hat is here. All right, let's change this title because it is no longer the 16th. It is Friday, the 18th. And we're doing a transport equation. Example. We'll bring this over to the other scene as well, because we're going to do some Matlab at the end. So get ready, get Matlab open so that you can follow along once we get to that. So we're going to do an example, and then we're going to go over to Matlab and talk about some symbolic tools. And we're going to try to do all of it in 50 minutes. I think it is achievable. All right, let's turn down the music just a little. Let's talk notation, shall we? So there's a lot of subscripts and superscripts flying around since we're starting to talk about velocity of an aircraft relative to different frames. And so I want to show you 4 cases below, and I want to break this down and we'll try to make it really clear. Okay, so look at this first case. We're going to do 4 of them, and we're going to talk about what the superscripts and subscripts mean in each case. Okay, so let's start with this right in here. So this velocity g relative to O, so let's write it in here. This is the velocity of the CG of the aircraft, which is at G. Relative to O. And O is the origin of the fixed frame. So that's what this part means in here. But let's start talking about this subscript right here that appears in front. That tells you from whose perspective this velocity is interpreted. So this is saying this is the velocity of g relative to O, but the superscript is telling you it's from the perspective of the fixed frame. And then we have this final subscript down here on the outside. And what this is talking about is when we put this in array notation, so we make a vector for that velocity, this is telling us that we're expressing this vector in terms of f-frame components. So, okay. I got to get the right tense here. Expressed in f frame. Oh, I botched that word. Frame components. Now, just because you write a vector in terms of the components of a certain basis, that doesn't mean it's from the perspective of that basis. And I know that sounds confusing, so I'm going to try to clear it up a little bit right here. So, okay, the velocity of g with respect to O from the perspective of the f-frame. Well, when I say from the perspective of, I mean taking the time derivative with respect to the f-frame. So let's do that. So this velocity, what it's really saying is if I take the time derivative with respect to the f-frame, that's what this superscript on the left is saying. And the velocity is the time derivative of the position vector. So r from g to O, that's the position vector. Oh, and by the way, this little equals with a triangle sitting on top, this means defined as. So I'm taking the time derivative of the position vector with respect to the f-frame, so from that perspective, and then I'm expressing it in f-frame components, so I'm projecting that vector along to the f basis vectors. And in flight dynamics, when the velocity is with respect to the fixed frame, and if it's expressed in f-frame components, we call them x dot, y dot, and z dot. All right, and we're going to do 3 more cases of this, so it'll make it hopefully more clear as we go what these subscripts are meaning. Okay, so we took the time derivative from the perspective of the fixed frame f, okay? Now, when you take the time derivative of a position vector with respect to a fixed frame, we call this the inertial velocity. And so case 2 below, this is still going to be an inertial velocity, but let's see if you can tell the difference. Okay, so this is case 2. See if you can recognize the difference. So, like reading these, we have okay, the velocity of g with respect to O, that hasn't changed. From the perspective of the F frame, so that superscript right here, that hasn't changed. This tells us that we're dealing with an inertial velocity. The time derivative is taken with respect to the F frame. Okay, the difference here is this subscript. We're now expressing that inertial velocity in B frame components. All right, let's write this out again. So I'm taking the time derivative from the perspective of the F frame of our position vector G relative to O, and we're just projecting that vector onto the B frame basis vector components. And in flight dynamics, we use these variables u, v, and w to represent the inertial velocity projected onto the body frame. And what's so important about these, we get these values from onboard sensors. So from body fixed sensors. So when we're picking up sensor measurements, can you explain what you mean by the perspective of the F-frame? Wouldn't the perspective be the components you use to define the velocity? Okay, so when I'm saying perspective, I mean that I'm taking the time derivative with respect to the F-frame. So maybe the language I'm using here isn't precise enough. Like, so this paraphrased is just time derivative with respect to F-frame. Now, the time derivative with respect to the F-frame just gives us a vector. But the important thing is a vector can be represented in many different frames. So that's the difference between case 1 and case 2. Case 1 was also the inertial velocity, which just is the time derivative of the position vector from the perspective of F. So it would be like you're just sitting on the ground, you're watching this plane fly away. So from my perspective, that's the time derivative. And then you can still project this into either body frame or fixed frame coordinates. Okay, it is tricky because what is the inertial, like think about this, like what is this saying, like the inertial velocity from B frame coordinates? So this is kind of like I'm sitting in the aircraft and I'm looking back towards that fixed point on the ground, and I can see that I'm moving away from that point on the ground. So there's still some velocity. Now, I have a different set of components, U, V, and W, from that perspective sitting on the plane that describe that velocity. It is tricky. All right, we're going to do 2 more cases, and these following cases will not be an inertial velocity. So that means the time derivative will not be with respect to the F frame, but rather the B frame. So, okay. It's important to note here, even though the vector is expressed in B frame components, it is still an inertial velocity because the time derivative was taken with respect to the F frame. And we're going to do a numerical example after we finish these cases, so that'll you'll get to play with some numbers to see this. Okay, so these next 2 cases, cases 3 and 4, these are not inertial velocities. So this is the velocity of G relative to O from the perspective of the body frame. Now I want to take back what I said earlier, like that perspective of sitting on the plane. Because what I described to you was the time derivative from the B frame. Which is not the inertial velocity. Okay, let's play this out. So the superscript on the left, the time derivative with respect to the B frame of our position vector G relative to O and then I'm going to project that onto F frame components. Okay, so let's break it down. Velocity of G with respect to O, but from the perspective of, so time derivative with respect to B frame. But I'm expressing that, I'm projecting that vector onto the F frame at the end. And in flight dynamics, we don't have specific variable names for these numbers. So I'm not even going to put variables in here. I'm just going to say, like, generally, you could project this onto the F frame and you'll get, you'll be able to populate that vector with a couple numbers. Okay, one more case, and then we're going to do an example with numbers, which I think will help. So this is the velocity of G relative to O. I'm taking the time derivative in the B frame, and then I'm projecting that into B frame components. And because it takes a little time to do those colors, we're just gonna do it like this. Position vector relative to the B frame. And then we also don't have specific variable names for this. So I'll call this like 4, 5, and 6. It's just, you'll get some numbers if you ever try to calculate this. But what I want you to, probably the most important thing to take away from this is which frame the time derivative is taken with respect to. And if that time derivative is taken with respect to the fixed frame F, we call it an inertial velocity. But you can express that inertial velocity in F or B frame components. And I think it's one of the trickiest things about kinematics, just to wrap your mind around. So we're going to do an example. Okay, so like I said, these last two cases, those were not inertial velocities. Okay, here's our example. Prepare yourself. Actually, I'm going to show you the picture first, and then I'm going to come back to these. Okay, here's like a familiar picture. We have the F frame with the origin O. That's just fixed. And then we have the aircraft moving around in the sky, and point G is at the CG. And these body frame axes are fixed to the aircraft, so as the aircraft moves around, BX will always be pointing wherever the nose is. So up above, I'm defining this position vector with respect to B frame components. And maybe this helps a little bit too. Like this position vector, if I project it onto B frame components, it's this, but I could also project that position vector onto F frame components. In any case, it just represents this vector in space. Okay, now this vector is a function of time. So there is some velocity. G is moving relative to O. So we're also given the relative angular velocity of the B frame with respect to the F frame. So that's what this notation is. This is the angular velocity of B with respect to F. So we can see that this is rotating about its BX axis relative to F. So we have the position vector, we have the angular velocity, and we have a third piece of information, which is the attitude of the aircraft at this instant, or the orientation. So attitude, we can express it with Euler angles, we could express it with quaternions, we could use a direction cosine matrix, but the point is we know where this thing is fixed in space right now. Okay, now we have all of these four cases of the velocity from above, and it's confusing. So we're going to try to use this example and calculate what all of these velocities are and see what's different about them. Okay, so that's our goal. Get all four of these different velocities. Superscripts and subscripts flying all over the place. Now we're going to use the transport equation to help us out. So this is the transport equation. All right. So the time derivative of the position vector with respect to the F frame is equal to the time derivative of that position vector with respect to the B frame. I'm going to copy this. Copy. And then this part. I'm going to take this from below. So this equation right here is the transport equation, or transport theorem. It relates the time derivative with respect to two different frames. So equivalently, so this vector on the left is the velocity with respect to the F frame, velocity with respect to the B frame, and then beyond this, we can then project these vectors onto different basis vectors. But that would be if we're using array notation, which we're not yet. Okay. So we're going to break this down. And let's look at this first term, which is equal to this. So this is what we're going to look at first. So this is what it means to take the time derivative of a position vector with respect to the B frame. Okay, so we got the time derivative of this position vector with respect to the B frame. And from the example prompt, this is the position vector in the B frame changing as a function of time, right? So what is the time derivative with respect to the B frame? Well, in the B frame, all of these basis vectors are fixed. They're not changing with time because relative to the B frame, these things are just sitting there. They're a part of it. But these functions, these are changing with time. So if I'm taking the time derivative of 250t should just be 250. Okay, that one's easy. The derivative of this term takes a little more work because we got to do like this product rule. So I take minus 10,000, and then I take the derivative of the inside of this sine function, which is going to be minus 0.1 e to the minus t. And then I have to take the derivative of this sine function itself, cosine 0.1 e to the minus t. So that's the time derivative of that portion. And then we're going to do the same thing for this BZ thing. So it's just like differentiating any function of time. Since we're in the B frame, the B basis vectors are fixed. Okay, so this one will be minus 10,000 times the derivative of the argument of the cosine function. And then the derivative of cosine is minus sine. So here's the derivative of that piece. And now we'll just simplify this out a little bit. So I have 250 bx. If you take 0.1 times 10,000, well, that's a tenth, so it just becomes 1,000. This is now positive 1,000 e to the minus t cosine 0.1 e to the minus t. And then this next term has 3 negatives, so it still comes out negative. 1,000 e to the minus t sine 0.1 e to the minus t. Okay, so we had to do a little bit of work there, but that's the time derivative of the position vector with respect to the B-frame. And now you can write this in B-frame components. Well, it's already there in B-frame components, but we're going to put it in array form. So 250 bx, 1,000 e to the minus t cosine 0.1 e to the minus t by, and then minus 1,000 e to the minus t sine 0.1 e to the minus t. Okay, and now you see all of these superscripts and subscripts at work. The time derivative was with respect to the B-frame, and then we expressed it in B-frame components. I want to skip ahead, and then we'll come back, but I could express this in F-frame components. So let's go down. I think I wanted... Okay. No, you know what? I don't want to screw up the order here. Let's just keep going in the order that I originally put in here. So we'll get to expressing this in F-frame. It's going to be a rotation matrix that takes us there. All right, so let's go back to the overall calculation of the velocity with respect to the F-frame. So from the transport theorem, it's this whole thing. We just calculated this part, the derivative with respect to the B-frame, so we got to do this angular velocity cross product. So let's calculate that. The angular velocity given in the problem statement, minus 0.1 e to the minus t. And that's about the bx basis vector. And then we're crossing that with the position vector, so there it is right away. Now, when you're doing this, multiplying all this out, you got to remember that if you take the cross product of two vectors that are the same, you're going to get the zero vector. Bx cross by, I'm going to get bz. And bx cross bz, I'm going to get minus by. And how am I getting this? I like to use this little figure. But basically, if I cross bx and by, in this direction it goes to bz. And if you go opposite the direction of the arrows, it gives you a minus sign. So if we went bx cross bz, we go opposite this arrow, and we get a minus by. Okay, so if we apply those rules when we do this cross product, we're going to get 1,000. So this is from crossing bx and by, those terms. I'm going to have 1,000 e to the minus t sine 0.1 e to the minus t along the BZ direction. Okay. Now I'm going to cross this BX term with this BZ term. So BX cross BZ is going to be a minus BY. And we already have these two minus signs, so it adds a third. So overall, it's going to be negative. So this is going to be minus 1,000 e to the minus t cosine 0.1 e to the minus t by. So we're doing the transport theorem, and this is the cross product portion that we get. Okay, so if you look carefully, most of this cancels out with the other term from the transport equation, because remember we're adding this term to this cross product. And let's compare that really quick. Where'd it go? So we'll remember this. We have 1,000 of this along the BZ direction. And maybe I can get them all in the same frame. There we go. So this, we're adding it to this and they cancel out. And same thing happens here with this by term. I have the negative of this, and then I'm going to add it up here. So that's going to cancel out. So all that we're left with when we add these two terms together is this guy, 250 along the bx basis vector. So from all of our transport theorem, it turns out that we're left with just this. So if we put this in array form, um, 250 along bx, 0 along by, and 0 along bz. So once again, this is the derivative of the position vector with respect to the F frame, but I'm expressing it in B frame components. So even though this is written in the B frame, it is the inertial velocity. Okay. Let's keep going. So let's say I want to express the inertial velocity in the F frame. I have it in the B frame. How can I get it in the F frame? Well, you're going to use a rotation matrix. So if I have this vector, I have to multiply it with the rotation matrix from B to F, and that product will give me the components along the F frame. So in the problem statement, so how do you get this rotation matrix? Well, we've derived it in class. We've parameterized it in terms of Euler angles. So you have that equation, that matrix equation written out in terms of Euler angles. So in the problem statement, we said these are our Euler angles. So if you plug them in to the formula for the rotation matrix, you're going to get this. We derived the rotation matrix from F to B, but up above you see that I need the rotation matrix from B to F. So how do you get that? You just take the transpose of this matrix. Because from B to F is the same as the transpose from F to B. So let's take the transpose of this matrix up here. basically you exchange the rows and columns. And the diagonal will remain the same, so I'll still have these cosines. So really all that happens in the transpose is that I'm going to alternate these two sine expressions. Minus sine 0.1, and then... So that's all you need to do to take the transpose of this. Okay. So then... if I want this inertial velocity in F-frame components, I just use this rotation matrix, multiply it by the same vector in the B components, and if we multiply that all out, well, it turns out to be the same. So that's kind of a rare case where the velocity is the same in either basis at this point. Okay, the last thing we're going to calculate, this is like our fourth case. This is the time derivative with respect to the B frame, but ultimately we write it in components of the F frame. So same deal. If I have it with respect to the B frame, then I just need to do the rotation matrix from B to F, multiply that out, and then I'll get it in the F frame. So I already took the liberty of taking that matrix that we already got, and then this rotation matrix. Let's just multiply that out. So I'm going to have this row times this column, so that row is easy. It just turns out to be 250. And then this next one, I'm going to have 1000 e to the minus t. Like I can like factor that all out. Cosine 0.1 times cosine 0.1 e to the minus t. And then it's going to be plus sine 0.1 sine 0.1 e to the minus t. So this is taking this second row and multiplying it with that column vector. So it's just doing some matrix multiplication. Okay, then let's do the last one. 1000 e to the minus t. This one's going to be sine 0.1 cosine 0.1 e to the minus t minus cosine 0.1 sine 0.1 e to the minus t. And then at whatever time you can plug in that number and get this vector purely in terms of numbers here. But I'm going to post this, so go back through this again on your own time and try to notice the differences between each of these vectors depending on which basis you take the time derivative with respect to, and then also in which basis you ultimately project the vector. I forgot the 1000 for the second term. He actually forgot the closing parentheses. To e to the minus t. Oh yes, yes. I was trying to be fancy with pulling out these common terms, and then I forgot the closing. Yeah, because it's that 1000 e to the minus t Yeah, thank you guys. I could either just close everything or I could distribute that 1,000. Yeah, thank you. Okay, so like I said, I'll post this. But now I want to go over to Matlab and I want to show you how to use the symbolic toolbox. If you haven't used it before, it's really nifty because in the most recent homework, I think you need to take the inverse of a 3x3 matrix, right? And you can do that by hand, but we want to start practicing symbolic tools. Actually, we might ask you in the homework to do it symbolically. Anyways, do it symbolically. Save yourself some headache. Wait, let's make this a little bigger. Okay. Let me show you the example I'm going to do. So let's go back to the surface really quick. Okay, now remember this. We have this relationship where this is the angular velocity expressed in B frame components. These are our Euler angles, and this is the matrix that relates them. But what we like to do is convert this equation into this form where we have the Euler angle rates by themselves. So the way you go from this equation up here to this one down here is you have to take the inverse of this matrix. Nobody wants to take the inverse of a 3x3. Please no more by hand, says Crispy Brownie. So I want to show you how to take the inverse of this specific matrix in Matlab. So that's what we're going to do. Okay. And I'll post this code for you guys too. But follow along right now. If you have Matlab in front of you, you could pull up Twitch on your phone and then code along. We're having a code along. Okay, so what we're gonna do. I like to start my code with a little clear all and close all. Inverse A? No, okay. Dilly, you gotta do a little more work than that, okay? It's not just inverse A. We're doing symbolic tools. Okay, so the way to initialize symbols in Matlab is you use the sims command. And this matrix was a function of theta and phi. So I'm making, Dilly says, damn, I thought it was just inverse A. No, you gotta do a little more work. But it's not much more work. Don't be intimidated by this at all. So the matrix was function of theta and phi. So I'm gonna define this matrix E321. I'm calling it 321 because it's in terms of the 321 Euler angles. And I'm defining the inverse of the 321 matrix first. So let me show you what the heck I mean. So, okay. This final matrix, after we take the inverse, we call that E. So I'm trying to get E, but I'm starting here. So I'm calling this the inverse of E. So I'm going to make this matrix right now. And like I said, it's only a function of theta and phi. Okay, I'm going back over here. So I'm building that matrix. So let's do it. It's 1, 0, minus sign, oh my goodness. Minus sign of theta, and then I'm going to go on to the next line. You can do this dot, dot, dot thing if you want to build across multiple lines. I like to do this for matrices, so it's clear to me which are the rows. And okay, so sign phi times cosine theta. All right, that's the second row. Another dot, dot, dot. We're going to the third row. 0 minus sine phi, and then cosine phi times sine theta. Let's just run this right now. In class 9/18/2020. Let's do this. Oh, okay. Because I made this one. E321 inverse. Oh, geez. You know what I forgot? I forgot to put these semicolons to actually make it go down row by row. Let's run this again. Yeah, remember these to terminate your row. My bad. Boom. Okay. Good. We made it. It is populated with symbols. And now, Dilly, it is as easy as you think. So E321 is just going to be the inverse of E321 inverse. Let's run that. Okay. And you notice it's at this point it's a little different than the matrix we've seen in the notes, right? I want this nice clean one. Wait, where did it go? You know, top row is 1 sine phi times tangent theta. Like what's going on in Matlab? Why don't I have that matrix? Okay, so here's a little trick. You say E321 equals simplify E321. And then it cleans it up for you. Let's see what that does. Wait a second. I think this one might be, what did I do? 1, 0, I'm checking this matrix because I might have just done it wrong. Cosine phi, sine phi, cosine theta, 0 minus sine phi, cosine phi. Oh my goodness. Good grief. This was supposed to be cosine theta. Okay, I had a little typo up there. That cosine got lost in translation. Okay, let's run this again. Let's not do the simplify command yet. Sometimes simplify doesn't make a big deal. Okay, let's... No, okay. So this is still a pretty big matrix that it's not exactly what I'm expecting to see. So now let's see if the simplify does indeed help out. Okay. So I fixed my typo up above, hopefully. Okay, this is much smaller, right? Now, let's look at this term, the 1, 2 element. Sine phi times sine theta divided by cosine theta. Well, okay, I know that sine theta divided by cosine theta is tangent, and Matlab didn't simplify this to a tangent. If I go back to this one, I know that I should have sine phi times tangent theta. Cool. In Matlab, I have sine phi times sine theta over cosine theta, so that is tangent theta. Okay. So we took the inverse of that matrix. Now, let me show you how to evaluate this matrix with numbers, because you're going to want to, in whatever code you're using, turn this back into a numerical matrix so that you can multiply it with some other vectors. So let's call this numerically evaluating the matrix. So let's assume that theta is 5 degrees, but we have to convert this to radians. And let's say phi is like 3 degrees. So that's phi in radians. It's 3 degrees just converted to radians. So here is how you substitute that into the matrix. Easy as this. So, okay. Remember, at the top, I defined theta and phi as symbols. So now, I'm redefining them with the same variable names as numbers. Now, when I do the subs command, it's going to recall E321, and it's going to substitute these values in and evaluate the matrix. So let's see what happens. Boom. Okay, so we see that those numbers for theta and phi are plugged in here. Now this still isn't exactly where we want it to be. Actually, I'm curious. Can I... Let's just make a random vector and see if I can multiply. So I'll call this like 1, 2, 3. It's a 3 by 1. Let's see if I can do... Okay, so you could do that, but you could multiply these together, but it's going to return this huge gobbledygook thing, which it can be nice for some applications. But let's say I want them to actually simplify this out into some decimal number. Here's what you can do. You go E321 equals double E321. Double doesn't mean double it or square it. It just means convert it into a double format. So that just means in like computer speak, a number with a certain amount of decimals. I forget exactly how many. Okay. So let's evaluate this. So now E321 is a matrix with just the good old numbers that we're used to. And so if I take that vector that I made earlier now and multiply with this, boom, I get back this. And then I can do your, your typical Matlab style calculations. So let's go back to the code real quick so you can see this. So real basic, define your symbols, define your matrix in terms of those symbols, and then you can use your inverse command and it'll make a symbolic matrix. So that's cool. But then what if I actually want to translate that matrix into a matrix full of numbers that I'm used to using in Matlab? Well, you have to define the numerical value for your symbols. You have to substitute those symbols into the symbolic matrix and then convert the symbolic matrix into double precision. And that's it. That's it. There's a lot of other cool stuff you can do with symbolic manipulation in Matlab, but that's all we're going to show you for now. And guys, that concludes our session for today. I hope you are less confused than when you came in. What do you mean by double precision? I think that's what it's technically called. Like, here, let's go to the internet. Like, it's called double precision floating point format. It's a computer number format, a data type with decimals, usually occupying 64 bits in computer memory. So that's all it means. double precision. There's all these other kinds of precision. Float, mini float. That's what I wanted to show you. You guys having a good Friday? Cool, learn something new every day, I guess. Yeah. Have a good weekend, Dilly. And the rest of you have a great weekend as well. Get some rest. Dr. Estes is the bestest. Hey, thank you. Hey, thank you, Flight Dynamics student. Thank you guys for your attention. Thanks for coming to class on a Friday afternoon. We'll try to keep it nice and informative. Give you some tools for flight dynamics. All right, everybody, I'll hang around for like just a couple more minutes. If you have any questions or thoughts, you're welcome to share them. You can just hang out, listen to some tunes. Friday evening, 10 p.m. Hate this virus? Wait, what's Friday evening, 10 p.m.? Wait, are you somewhere where it's 10 p.m. right now? Oh, where are you? 10 p.m. Belgium. Oh, cool. Well, I'm glad you're here, hanging out on a 10 p.m. Friday night. Wait, are you a UB student? Or are you just hanging out? Which you're welcome to in any case. Belgium. That is awesome. Dutch, French, and German. Mostly Dutch and French speaking. Not a student, just stumbled onto your channel and the title piqued my interest. Cool. Well, we're here at this time, Mondays, Wednesdays, and Fridays. So you're always welcome to come. Next week, we're getting into the equations of motion for aircraft. So we're doing all of Newton's laws. It's a good time. Belgium is a constitutional popular monarchy and a federal parliamentary democracy. That means Belgium has a king. Cool. Actually getting my PPL so it relates. Ooh, your pilot license. Private pilot license. King, yes, but it's more ceremonial. No real power. Okay, good to know. All right, everybody. I think I'm going to peace out of here. B. Hermans, thanks for hanging out. Joining all the way from Belgium this Friday night. You have a great weekend, my friend.